Welcome back. The plan is built, the scope is drawn, the questions are sharp. Now comes the heart of fieldwork, gathering the evidence that turns audit questions into audit conclusions. This chapter is where auditing gets tangible and AI adds fascinating twists to techniques you may know from traditional audit. Here's our focus map. First, sampling in an AI world. Statistical sampling versus full population testing, and why AI sometimes lets you abandon sampling entirely. Then the specialized approaches, demographic stratification and fairness-focused sampling, output sampling, counterfactual testing, and anomaly-based selection. Second, the classic evidence gathering methods, refreshed for AI. Document review of architecture diagrams, model cards, and test results. Walkthroughs and technical testing. Interviewing data scientists, and designing synthetic test cases with honest coverage assessment. Third, the quality bar. Verifying evidence completeness, integrity, and timeliness, and the special complications of consent and cross-border compliance when the evidence itself is personal data. And fourth, the analytical edge. Trend analysis, pattern recognition, statistical testing, and using predictive analytics to spot emerging audit risk before it becomes an incident. Good evidence is the difference between an opinion and an assurance. Subscribe if you haven't, and let's gather it properly. Let's begin with a question that AI genuinely transforms. How much do you test? In traditional auditing, sampling exists because testing everything is impossible. You can't manually reperform 10,000 transactions, so you test a representative sample and infer. But AI quietly hands us a superpower, and understanding when to use it is the heart of this lesson. First, the traditional logic, because it still applies in parts. Statistical sampling selects a subset with enough rigor that conclusions about the sample extend with known confidence to the whole population. The discipline matters: sample size, selection method, confidence levels, and the reason it exists is human limitation. Testing everything by hand is infeasible. Now the AI superpower. When the thing you're testing is itself computational, you can often test the entire population because the machine that made 10,000 decisions can be asked about all 10,000 at once. Want to know the model's approval rate across every demographic segment? You don't sample, you compute it over the full decision history. Want every case where the model and the human reviewer disagreed? Query them all. This is full population testing, and it changes the epistemics of audit. No sampling risk, no inference gap. You're not estimating the fairness metric, you're measuring it exactly. I find this genuinely exciting. Whole categories of audit uncertainty simply dissolve when the population is data and the analysis is code. So when do you still sample? When full testing isn't feasible or isn't the point. Manual verification. If each case needs a human to check the decision against source documents, remember label accuracy from Chapter 10, you're back to human limits. Sample. When you do sample, how you select shapes what you can see, and nowhere does this matter more than fairness. Today, demographic stratification and fairness-focused sampling, the techniques that ensure your evidence can actually detect the discrimination you're looking for, because a naive sample is beautifully capable of hiding it. Start with the trap. Suppose you take a simple random sample of a model's decisions to assess fairness. Sounds rigorous, right? But if a disadvantaged group is, say, 5% of the population, a random sample of 200 cases gives you roughly 10 of them. Far too few to say anything reliable about how the model treats that group. Your sample faithfully mirrors the population, and in doing so, inherits its blindness to minorities. Remember Chapter 10, representativeness cuts both ways. And the very groups most at risk of harm are the ones random sampling under-observes. So the honest fairness assessment came back clean, Not because the model was fair, but because you never looked hard enough at the people it might hurt. The fix is stratified sampling, deliberately dividing the population into subgroups, the strata, and sampling enough from each to draw reliable conclusions about all of them. For fairness work, you stratify by the groups whose treatment you must evaluate. Demographic groups where lawful and available. And critically, the intersections from Chapter 14, older women, specific regional ethnic combinations, because that's where discrimination concentrates and hides from single attribute views. You deliberately oversample small but important groups, accepting that your sample no longer mirrors the population precisely, because the goal isn't to describe the population, it's to test the model's behavior on everyone it affects. Beyond stratifying by who, AI offers evidence selection techniques that traditional audit never had because we can interrogate the model directly. Today, three of them: output sampling, counterfactual testing, and anomaly-based selection. Each answers a different question, and together they're a large part of what makes AI auditing its own craft. Output sampling shifts the focus from the population of past decisions to the space of possible outputs. Instead of only reviewing what the model decided on real cases, you sample across the range of its behavior: high confidence and low confidence outputs, decisions near the threshold boundary where small changes flip outcomes, and the extremes. Why? Because the boundary is where the model is least certain and most consequential. Remember Chapter 1. Someone chose that threshold, and the cases sitting right on it are where the choice bites hardest. Reviewing a spread of confidence levels also lets you sanity check calibration from Chapter 14. Does the model's stated confidence match reality across its range? Counterfactual testing is the technique I find most powerful, and it's uniquely available with AI because you can ask the model, what if? You take a real case, change one attribute, and observe whether the decision changes. Change the applicant's gender while holding everything else constant. Does the outcome shift? Change the postal code, the name, the age? This directly probes for discrimination and proxies, remember Chapter 10, in a way no observational sample can, because you're running a controlled experiment on the actual model. A famous pattern: flipping a name from one that reads as one ethnicity to another and watching the score move, is counterfactual testing catching bias red-handed. The auditor's caution: counterfactuals must be realistic and carefully designed, and a single flip rarely proves systemic bias. You run many, across many cases, and look for patterns. Anomaly-based selection abandons randomness entirely to hunt the unusual. Instead of representative cases, you deliberately select the outliers, the decisions that don't fit expected patterns, unusual score distributions, cases where model and human sharply disagreed. Remember Chapter 13's override signal, or clusters of similar odd outcomes. The logic: problems concentrate in anomalies, and while stratified sampling ensures fairness coverage, anomaly selection ensures you find the specific broken things. It's the difference between surveying the whole field and following the trail of disturbed earth. Let's return to the most traditional evidence-gathering method of all: reading the documents. Because for all AI's novelty, a great deal of audit evidence still lives in artifacts people wrote down. The twist is knowing which AI documents matter and, more importantly, how to read them like an auditor rather than a librarian. Start with the three artifact families this course has already taught you to value. Architecture diagrams show how the system is actually built. The three layers from Chapter 2, the AP1s and downstream dependencies, where data flows, where humans sit, where the boundaries are. Read them to understand the system, yes, but also to find what's missing. A diagram with no logging component, no human review step, no monitoring feedback loop tells you as much by absence as by presence. Model cards and dataset cards, remember Chapter 10, are pre-answered evidence requests, documenting purpose, training data, performance across segments, and limitations. A team that maintains them honestly has done half your thinking for you, and the limitation frankly stated, like not evaluated for under 18s, becomes your evidence when you find the system deployed to students. And test results. Remember Chapter 14's whole documentation lesson, the validation reports, fairness analyses, and red team findings that either substantiate the organization's claims or reveal their absence. Now the auditor's reading discipline. 3 habits that separate review from reception. First, read for currency. Remember the museum plaque problem. Check dates and versions against the change log. A model card describing an ancestor that retrained 5 times ago is documentation of a system no longer running. Second, read for honesty. Does the documentation preserve failures and ugly segments, or is it suspiciously triumphant? Remember, a test record with no failures describes either a perfect team or a curated one. Third, read for traceability. Can you follow a claim from the summary down to the raw evidence and back up to the approval that relied on it? The vertical slice from Chapter 6 that reveals whether frameworks connect or just coexist. Documents tell you what should be true. Now we find out what is true through 3 active methods: walkthroughs, technical testing, and interviews. This lesson is where you leave the reading room and engage the living system and the people who run it, and it's where the best evidence and the most revealing surprises tend to emerge. Walkthroughs first, the method of following something all the way through. You pick a real case or a change or a decision and trace it end to end through the actual process, watching each step happen. Walk a single loan application from data intake, through the model, through any human review, to the customer notification and any appeal. Remember Chapter 2's plumbing. Walkthroughs are how you find the gap between the diagram and the reality. I love walkthroughs because they expose the undocumented, the manual workaround nobody mentioned, the review step that's technically there but functionally skipped, the handoff where accountability evaporates. Ask the person to show you, not tell you, and watch what they actually click. Technical testing is direct examination of the system's behavior, and here you deploy the whole arsenal from Chapters 14 and this chapter's sampling lessons. Run the counterfactuals yourself or observe them run. Query the full population for the fairness metric. Test the edge cases. Probe the guardrails. Reconcile the configuration baseline against production. Remember Chapter 12. The principle: wherever you can generate evidence directly, rather than accepting the organization's own testing, do, because independent evidence is the strongest evidence. Effective challenge from SR 11-7 made literal. Interviewing data scientists is its own delicate art, and Chapter 16's engagement lessons apply in full. Your goal is understanding and evidence, not interrogation, and the posture that works is genuine curiosity anchored by clear audit questions. The techniques I rely on: ask them to explain their choices. Remember, why this algorithm, why this threshold, and listen for whether the answer is reasoned or reflexive. Ask about what worried them. Good data scientists have doubts about their own models, and a defensive claim of no concerns is itself informative. Ask, what would you do if this failed tonight? The 2 a.m. test from Chapter 6, surfacing whether ownership is real. And when jargon rises as a wall, translate rather than nod. So what you're telling me is, remember Chapter 16, both to genuinely understand and to gently show your following. Sometimes the evidence you need doesn't exist in the organization's records, so you have to create it. Today, designing synthetic test cases, deliberately constructed inputs that probe exactly the behaviors you want to examine, and coverage assessment, the discipline of knowing whether your tests actually reached everywhere they needed to. Careful here, this synthetic means crafted test inputs, not the synthetic training data from Chapter 10. Related idea, different job. Why design your own cases rather than rely on real ones? Because real decisions only cover situations that actually arose, and the situations you most need to test may be rare, sensitive, or absent from history. Want to test whether the lending model treats two otherwise identical applicants differently by gender? Real data rarely gives you clean matched pairs, so you construct them, the counterfactual technique from earlier, systematized. Want to test edge cases the system hasn't yet met? The 102-year-old applicant, the transaction exactly at threshold, remember chapter 14? You design them deliberately. Want to test harmful content resistance in a generative system without waiting for a real user to try? You craft the probes, the red teaming logic from chapter 15. The craft of good synthetic cases has principles worth holding. Realism. Cases must be plausible enough that the model's response is meaningful. An absurd input teaches you little. Purpose. Each case should target a specific audit question. This case tests proxy discrimination. This one tests the OOD handling. This one tests the guardrail. Controlled variation, especially for fairness. Cases that differ in exactly one attribute, so any behavior difference is attributable. And systematic construction, not a handful of ad hoc examples, but a designed suite covering the space of concern, which brings us to coverage. Coverage assessment is the honest reckoning. Did my testing actually reach everywhere it should have? It's easy to run many tests and still have blind spots. Plenty of cases clustered in the easy middle, none at the dangerous edges, or every demographic tested except the intersections. So mature evidence gathering maps tests against a coverage frame. Which risk areas, which segments, which edge conditions, which failure modes did I probe, and where are the gaps? Remember chapter 14's warning. Running many tests is not the same as testing thoroughly, and the untested corner is exactly where the incident waits. We've gathered evidence many ways. Now we hold it to a standard, because not all evidence is equally trustworthy, and an audit conclusion is only as sound as the evidence beneath it. Today, 3 quality dimensions to verify on everything you collect: completeness, integrity, and timeliness. These aren't abstract virtues. They're the questions a skeptic or a regulator will use to attack your findings, so verify them before someone else does. Completeness asks, is this the whole picture or a curated slice? The risk is selective evidence, and AI makes it easy. An organization showing you the model's performance on the segments where it excels, the test results that passed, the months where drift stayed calm. Your defense is knowing what complete would look like. Remember success criteria from chapter 16 and probing for absence. When someone provides fairness results for 3 demographic groups, ask about the 4th. When test documentation shows no failures, remember that's a flag, not a comfort. And prefer full population evidence where you can get it. Remember lesson 1. It's complete by construction, no curator between you and the truth. Integrity asks, is this evidence genuine and unaltered? Traditional audit worries about doctored documents. AI adds subtler concerns. Was this test result actually generated by the production model or by a different version? Remember chapter 14. Results without version identity are often numbers. Are these logs tamper evident, or could the model team have edited them? Testimony from an interested party. Is this dashboard showing live data or a screenshot from a good day? Your techniques. Prefer evidence generated automatically and stored immutably over numbers hand-typed into slides. Verify against source systems where you can, and remember the reproducibility standard. Evidence you can regenerate yourself is integrity you can prove. Timeliness asks, does this evidence describe the system as it is now? This is AI's special quality trap. Because systems drift and retrain, remember the museum plaque one final time. Fairness testing from before the last retrain describes an ancestor. A monitoring screenshot from last quarter may bear no relation to today's behavior. So every piece of evidence carries an implicit as of date, and your job is checking that date against the change log from Chapter 12. Evidence about a model must post-date that model's current version, or it's evidence about something that no longer exists. Here's a twist that catches auditors off guard. The evidence you gather to audit AI is often itself personal data, and gathering it can create the very compliance problems you're investigating. Today, consent and cross-border considerations in your own evidence handling. Because an auditor who breaches privacy while auditing for privacy has failed in a particularly embarrassing way. Think about what AI audit evidence actually contains. Decision records full of customers' personal data, the loan applications, the claims, the profiles. Model training data, remember Chapter 8, personal and sometimes sensitive. Prompt and conversation logs, brimming with whatever users typed. Demographic data you gathered for fairness testing, which may be sensitive attribute data, ethnicity, health, the most protected categories of all. When you pull all this into your working papers, run analytics on it, or feed it into tools, you are now processing personal data, and the principles from Chapter 8 apply to you. So the consent and lawful basis question turns inward. Does the organization have a basis for you to access this personal data for audit purposes? Usually, yes. Audit is a recognized, legitimate purpose, but it should be considered, not assumed. For the demographic data especially, remember Chapter 9's tension. If the organization couldn't lawfully collect sensitive attributes, you may face the same constraint in gathering them for fairness testing. And the workarounds, proxies, aggregated analysis, privacy-preserving techniques become your methods too. And purpose limitation applies to your working papers. Evidence gathered for this audit shouldn't casually become a permanent personal data store. Now, cross-border, the dimension teams forget until it bites. Remember Chapter 8. Where does your audit evidence physically go? If you're an external auditor in one country, examining data governed by another's rules, transferring that evidence to your systems may itself be a regulated cross-border transfer needing a lawful mechanism. If your audit tools are cloud-based, where do they process the data? If your team spans jurisdictions, does sharing working papers move personal data across borders? I've seen an audit inadvertently create a transfer violation by uploading EU customer records to a tool hosted elsewhere. The audit of compliance becoming a breach of it. Now we sharpen the analytical edge because gathering evidence is only half the work. Making it speak is the other half. Today, 3 analytical techniques that turn raw AI evidence into findings: trend analysis, pattern recognition, and statistical testing. These are where the auditor stops describing what happened and starts demonstrating what it means. Trend analysis looks across time, and AI systems, remember, are deeply temporal. They drift, they're retrained, they decay. So plotting metrics over time reveals stories a single snapshot hides. Is model accuracy quietly declining month over month, the slow rot from Chapter 3? Are complaints about AI decisions rising? Did a fairness gap widen after a particular retrain? Remember Chapter 12, connecting the trend to a change. I once found a model perfectly acceptable at the point I examined it until I plotted 6 months of its approval rates and watched a clear drift the organization's own monitoring had never charted. Remember Chapter 13, the trend was the finding. Always ask of any metric, what does this look like over time and against what change events? Pattern recognition looks across cases for structure, the clusters and correlations that individual records don't reveal. Are declined applications concentrating in particular postal codes, a proxy signal from Chapter 10? Do the model's errors cluster in a specific segment? Remember, harm hides in segments, and patterns are how you find it. Do override cases share a common feature, telling you where humans systematically distrust the model? This is where the anomaly-based selection from earlier pays off. Patterns in the anomalies point straight to root causes. Modern data analytics tools make this powerful, but the auditor's judgment decides which patterns matter and which are noise. Statistical testing is what turns an observation into evidence that survives challenge. And this matters enormously with AI because auditees will contest your findings. You notice the model approves one group at a lower rate, the team responds. That's just random variation. Statistical testing answers the challenge. Is this difference large and consistent enough to be real, or could it plausibly be chance? Significance testing, confidence intervals, effect sizes, these convert "this looks unfair" into "this disparity is statistically significant and unlikely to be random," which is a finding that holds under pressure. Remember the 4/5 rule from chapter 14, itself a statistical screen. The caution: statistical significance isn't practical significance. A tiny disparity can be statistically real yet immaterial, and a large one in a small sample can be real harm you can't yet prove, so pair the numbers with judgment. We close this evidence chapter by looking forward instead of back, because the best auditing doesn't just find problems that happened, it anticipates problems that are forming. Today, using predictive analytics to spot emerging audit risk, turning the very techniques we audit into tools that make audit sharper. There's a pleasing symmetry here, the auditor using prediction to watch the predictors. First, the shift in mindset. Traditional audit is largely retrospective. We examine what occurred and opine on it. But AI systems generate rich, continuous data about their own behavior. Remember all the monitoring from chapter 13, and that data carries early signals of trouble forming. The insight: many AI failures are preceded by detectable drift in the indicators. So an auditor watching the leading signs can flag risk before it becomes an incident, before it becomes a finding, before it becomes a headline. This is audit moving from autopsy toward early warning. Where does prediction help in practice? Consider a few honest applications. Watching drift trajectories, not just whether a model has drifted, but the rate and direction. Projecting when it will breach tolerance. Remember chapter 13's thresholds, so attention arrives before the breach. Analyzing patterns across the model portfolio to predict which systems are most likely to develop problems. Models with certain characteristics: aging training data, weak monitoring, high change frequency. Remember chapter 16's risk times uncertainty, are statistically likelier to fail. And prioritizing audit attention toward them is predictive risk-based auditing. Spotting leading indicators in operational data, rising override rates, creeping complaint volumes, widening segment gaps, each a smoke signal before the fire. And in continuous audit programs, our next chapter, predictive models that flag anomalies for human auditor attention automatically. But hold the professional cautions firmly, because you know them better than anyone by now. You've spent a whole course learning them. Prediction is probabilistic. Remember chapter 1. These signals suggest elevated risk. They don't prove problems. So they direct attention. They don't replace investigation. The tools carry their own biases and blind spots. A predictive audit risk model can itself be miscalibrated, so validate it as you'd validate any model. And the human auditor remains in command. Remember the theme of this entire course: prediction organizes and prioritizes, judgment decides, and accountability rests with you. Here's the closing thought that carries us into chapter 18. We've spent 17 chapters learning to audit AI, and now AI is becoming part of how we audit, watching, flagging, predicting. The relationship is turning reciprocal, and using AI well in our own craft demands exactly the discipline, skepticism, and human oversight we demand of every organization we examine. Next chapter, we tackle the hardest technical challenge of all: seeing inside the black box, explainability, and the audit tooling that supports it. See you there.